Okay, so in this next video, we're going to explore some of the properties of the inverse of a matrix, and we'll see that the way to do this is making use of this invertible matrix theorem. So if you need a reminder on the invertible matrix theorem, you can jump back to the previous video, but the main thing to remember is that if we're trying to establish that a particular matrix is invertible, it's enough to come up with this sort of equality here, right? If I find two matrices, and it's important that they're square matrices, okay? All of this is false if A and B are not square matrices. But as long as I have square matrices whose product is the identity, I can immediately conclude that A is invertible, that B is invertible, that B is the inverse of A, right? So B is equal to A inverse, and that A is the inverse of B, right? So A is equal to B inverse. Right. As soon as I have two things that multiply together, they're equal to the identity. And one of the things you can do, right, if you put these two together, this tells you that, well, the inverse of the inverse, right, well, that would be equal to, if B is equal to A inverse, right, then A inverse is B inverse, but here we see that B inverse is equal to A. Right. So there's one property that we have already. The inverse of the inverse is the original matrix. Taking the inverse twice puts you back where you started. Okay, good. Well, that's one result. We got that fairly easily from our theorem. Here's another one. Right. Here's one that it's kind of a silly result, but how would we do this? Prove that if a to the seventh equals the identity, okay, so we have some sort of result, some property that's given to us about this matrix, in this case a to the seventh is the identity. We want to prove that based knowing only this, it follows that a must have an inverse. How do we know that a is invertible? Well, if you know your laws of exponents, we know that a to the seventh is a times a to the sixth, right? A is a to the 1. So if we do a times a to the sixth, that by definition is a to the seventh. But we also know that a to the seventh is the identity. And so referring to what we have up above, we can see that a is invertible. And we also know what the inverse is, right? The inverse is the matrix we've found, so that multiplying by a gives the identity. What is that matrix? It's a to the sixth. Okay, so now we know that our matrix has an inverse, and we know what the inverse is. It's a to the sixth. So in principle, whatever this matrix A happened to be, once we know that a to the seventh is the identity, if we calculated a to the sixth, we would have the inverse of A. Let me squeeze in one. Let's see if we can squeeze in another example. Right here. If a squared is invertible, then so is a. Proof? Well, what does it mean to say that a squared is invertible? We have some matrix B such that if I do B times a squared, I get the identity, right? But B times a squared, what's one way I can rewrite? I could write that as B times A times A. Alright, and what do I have here? I have something multiplied by A giving me the identity. So what must that something be? That something must be the inverse. So these are the sorts of arguments you can make very quickly using the invertible matrix theorem. Okay, let's come up with some general arguments. First of all, we'll prove that the inverse is unique, right? one of the things you might worry about in this previous slide, these examples on the previous slide, is okay, sure, so a times a to the 6th gives me the identity. How do I know that this matrix a to the 6th is the only one that works, right? How do I know there isn't something else that might work? Well, we know that because there is only one inverse for a given matrix. And the way to see this is to say, okay, suppose I have two matrices, B and C, that both satisfy the definition of the inverse. So A times B gives me the identity, A times C gives me the identity, and of course that's true in either order. Well, here's a simple chain of equalities showing that B must be equal to C. Okay. First thing, we know that multiplying by the identity does nothing, so B equals B times the identity, right? But we have all sorts of things here which are equal to the identity matrix. And in particular, A times C is equal to the identity. Okay. One of the other things we know about matrix multiplication is that placement of brackets doesn't matter. By associativity, I can write that as B times A times C. But I also know that B times A is the identity, so this is the identity times C. And multiplying by the identity, well, that leaves me with C. So there you have it. B is equal to C, and this tells me that there's only one inverse possible. Okay, moving forward, let's look at a couple other examples, some other things that we can conclude with the inverse of a matrix. First of all, we can conclude that if we have two invertible matrices, then their product must also be invertible. In fact, this is an if and only if, okay? If I know that the product is invertible, then A must be invertible and B must be invertible. How do we see this? Well, let's take care of the first order, okay? So let's suppose that A and B are invertible. So suppose that A inverse and B inverse exist, right? These inverses are unique, so I can unambiguously write down A inverse and B inverse. So how do I show that A times B is invertible? Well, if A times B is invertible, that means I need to show that A times B is invertible, I need to come up with some other matrix C so that AB times C gives me the identity, right? The invertible matrix theorem says if I can find a C which does this job, then immediately I know that A times B must be invertible. All right, well, let me give you an example of such a C. Here it is. I'm going to let C equal to B inverse times A inverse. Why does that work? It works because I'm allowed to move brackets. B times B inverse times A inverse. Okay, but B times B inverse is the identity. Okay, I've got A times the identity times A inverse, but multiplying by the identity does nothing, so this is just A times A inverse, and A times A inverse is the identity. So that tells me two things. It tells me that AB is invertible, and that the inverse of a product is the product of the inverses. But note that the order is reversed. Okay? So when you take the inverse of a product, you have to change the order. Remember that the order of multiplication matters for matrices, right? If I multiplied by, if I did, let me stick it up here. If I did A times B times A inverse times B inverse, this is something which you can't simplify. This does not reduce to the identity in general, okay? Because in order to reduce to the identity, I would have to combine A with A inverse, but there's a B in between them, right? A is not next to A inverse. I can only say that A times A inverse is the identity when those two matrices are adjacent. If there's something in between them, I'm not allowed to rearrange to get A next to A inverse, and so there's no simplification that's possible here. So that wouldn't work. This is not the right inverse. This is. B inverse times A inverse, right? If you think of matrix multiplication as a function, then this makes sense, right? If you do two processes one after the other, and then you want to undo those processes, then you have to undo the most recent one first, and then work your way back, right? If your, let's say your two processes are, I don't know, putting on your socks and then your shoes, right? The inverse would be removing them. Well, you can't remove your socks before your shoes. The shoes have to come off first, right? So you've got to change the order. When you undo in the opposite order, okay? Now, this wasn't if and only if. How do I do the other direction? Well, the other direction is just a little bit of hocus pocus, I guess, with associativity. If AB is invertible, then we know that AB times AB inverse is equal to the identity, right? But be careful, here all I know is that AB is invertible. I haven't yet told you that B and A are invertible, so I can't actually write yet this as a B inverse times A inverse. I can't rewrite that inverse, but I can rewrite this guy as A times B times AB inverse equal to the identity, and now I've written it as A times something equal to the identity, and the invertible matrix theorem tells me that A must be invertible. Similarly, I could say that the identity is equal to A B inverse times A B, and I can move my brackets like so, right? And then I have something times B equal to the identity, and that tells me that B is invertible. And again, we're done. Okay. So that takes care of products, right? So now we know if we multiply two invertible matrices together, the product will also be invertible. Here are some other properties of the inverse to make note of. The second one we already took care of. The first one, well, the first one is easy. Let me give you a proof of one. And again, we're going to rely on the invertible matrix theorem for the proof. Okay, there's, I don't know what that, this is an extra bracket, ignore that bracket. So the inverse of K times A is 1 over K times A inverse. Why do I know that? I know that because if I take, remember all I have to do is show that these multiply to give me the identity. So I take K times A, I multiply by 1 over K times A inverse. I know that I can bring scalars out, so this is K times 1 over K times A inverse, but I know that K times 1 over K is just 1. I know that A times A inverse is the identity matrix, and multiplying by 1 does nothing, so I'm left with the identity matrix, right? So again, the reason why 1 over K times A inverse is the inverse of K times A is that when I multiply them together, I get the identity. The proof of 2 we already did. For 3, well, the proof of 3, I guess, is probably best done by induction, but let's just say that 3 follows from the product rule. Right, so the product rule for inverses, right? A to the n is A times A times A times A times A, and so the inverse is going to be, well, A inverse times A inverse times A inverse. I guess technically you should reverse the order, but they're all the same here, so reversing the order doesn't do anything. Okay, so those are all the properties that we want to look at for now. In the next couple of videos, we're going to look at what are called elementary matrices.